Today we're going to take a brief look at SystemC from the point of view of the experienced Verilog designer. This is not a presentation that is entirely about comparing the SystemC and Verilog languages. There's certainly some of that, but the main focus I'm trying to take is to compare how you would achieve a specific task in both languages. As such, the presentation is not so much focused on which constructs in SystemC are syntactically or semantically equivalent to various constructs in Verilog. Rather, I want to focus more on comparing the common implementation methods for synthesis-based design in the two languages. We'll start off with some of the conventions of SystemC and talk about how we commonly organize our code into multiple files. Then we'll look at a small example implemented in Verilog RTL and in SystemC behavioral code, something appropriate as input to a high-level synthesis tool, which is the main design path for SystemC coders. Then we'll end up with a rundown of some specific language constructs. So let's dive right in and talk about some common conventions we find with SystemC. Firstly, it is important to note that SystemC is essentially an extension to the C++ language. Thus, everything you can do in C++, you can also do in SystemC. In addition, SystemC includes special constructs to help you more appropriately model hardware, including such things as concurrency, modularity, hierarchy, and bit accuracy. When looking through the SystemC code presented today, you will notice that many of the internal names begin with SC underscore. No big mystery. This stands for SystemC. You will see this in such things as the module declaration keyword SC module, as well as with some simple data types like SC uint for unsigned integers and SC fixed for fixed point data types. Thankfully, the most basic top-level encapsulation construct in both SystemC and Verilog is called the module. In the Verilog language, the module keyword is actually module, and in SystemC it is SC module. Before we dive into a concrete example, let me first cover a couple of points about the file organization for modules. For most simple modules, like the one we are going to look at today, Verilog designers will put the entire module in a single file. The SystemC designer will typically follow the C++ coding conventions and split the module into two separate files, one being for a header file, normally with a .h extension, and a code file, normally with a .cpp or a .cc extension. I thought it would be best to use a very trivial example as a vehicle to demonstrate how to transition from Verilog RTL coding to SystemC. Along the way, we'll learn some key SystemC keywords and constructs, and see how basic functionality implemented in Verilog would be implemented in SystemC. The basic functionality we want to implement is 1. A very simple input protocol that handshakes with the test bench. 2. A trivial data path function that will add two numbers together to produce a result based on a select signal. All of the values used in this calculation, including the select signal, are inputs to the design. And 3, a very simple output protocol that handshakes with the test bench. So let's take a look at the Verilog code we might write to implement our tiny example. For the moment, let's restrict our focus to the definition of the module itself, as well as the ports and internal variables. Here we see the Verilog keyword module, followed by the user-defined name of the module. In the parentheses, we have a list of all the port names. Next, we see a list of the port definitions. Each one includes the direction of the port, the name of the port, and optionally, some specification of the width of the port. The internal variables are all defined using the reg keyword in this case, and includes the variable name as well as an optional width specification. Here we see how we might declare the same kinds of objects in SystemC. This file is the header file I mentioned earlier and contains a definition of a SystemC module, along with all the ports and internal variables. The module is declared via the SC module keyword, and we define the name of the module in the parentheses. Next, we see a list of port declarations. You will notice that each port declaration contains 3 key components. The direction specifier, which in our example is either SC in or SC out. Next comes the data type of the port. In the example code, we see a number of data types for the ports. Bool is a simple Boolean value that can only be true or false, representing the values 1 or 0. SystemC also has a bit data type that could be used in this context as well. We also see some unsigned integer types here along with the width specifiers for those integers. The third key component is, of course, the port name. So to summarize, each port has a direction, a data type including width, and a name. This is very similar to the Verilog port definitions we saw earlier. Here we see a side-by-side of some of the lines for each code sample we've just seen. I've removed some lines to make comparison easier. Again, the module definitions are very similar, except that in Verilog you include all port names in the module definition itself. Port definitions then follow, again, very similar for the two languages. Internal variable definitions follow that. Let's go back to our Verilog code and look at how we define a concurrent thread or process. In our case, we have used the always@posedge_clock construct. This defines a concurrent block that is synchronized to the positive edge of the clock. The reset code for this always block is explicitly written by the user. It tests for an active reset signal and will reset the important output ports when this case is detected. If reset is not active, we will go off and execute our state machine code. This kind of structure will be very familiar to Verilog designers. Now, if we look at the SystemC code to perform this same function, we will find that we need to look at the declarations in the C++ header files, as well as the functional code in the CPP file. Let's start by looking at the definition portion in the SystemC header file and take a look at the rest of the SystemC module definition. Here we see a new keyword called SCCTOR. This keyword represents a SystemC constructor function. In SystemC, the module we are defining is actually a C++ class, and classes in C++ have special functions called constructors. These functions are executed whenever a variable is created that has the specified class type. In our example, we also see a definition of a new object type with the SCCthread keyword. This represents a SystemC clocked thread. It takes two arguments, a function name that will contain the behavior of the thread and the active edge specification. Creating a connection like this between a function and a thread means that the function will be executed in parallel to all other execution objects in a SystemC simulation. We use this thread construct in our example in the same way we would use the always@posedge_clock construct in the Verilog code. The reset signal and the active sense of that signal is also declared here with a thread. If you want to have multiple threads in the module, you would declare them all here. Each must have a function associated with it that implements the actual behavior required. Lastly, we simply define a function called thread0, which will implement the actual behavior of the thread. The name of this function can be pretty much whatever you choose as long as it's legal C++. Over in the CPP file, we see the actual functional code of the SystemC thread. This function is split into two main pieces: an initial chunk of code that represents the reset code, a while-one loop that represents the standard operation of the thread. Now, it's important to understand the execution model of the SCC thread to which this function belongs. When simulation starts, or whenever the reset signal becomes active, execution of this function will begin at the very top, no matter where the thread was currently suspended. This means that the piece of code before the while loop is essentially the reset code. Once the reset code is complete, we enter an infinite loop that represents the function of the thread. In this portion of the code, you will see a number of wait statements. This means suspend this thread until the next active clock edge. This piece of code shows how we would represent the always@posedge_clock functionality in the Verilog code. Okay, so now it's time to look at the actual functional code for our little design. Now I realize there are many ways to implement this design in Verilog, so please don't focus on that. We're more interested in the language constructs for the moment. The structure we've chosen for this implementation is a very simple state machine. The first state implements the input protocol, followed by the state in which we will calculate our arithmetic result. The following two states implement the output protocol. At the end of the module, we have a very simple always block that updates our state variable. As in the Verilog, Here in the SystemC code, the functional part of our design has three main sections: the input protocol, the operation, and the output protocol. Looking at the input protocol, we first assert a request for data and then wait an indeterminate number of clock cycles until data is ready. We then read all the inputs. The wait statement you see here says, wait a clock cycle. The operation we need to perform comes next. This comprises a simple if statement and a couple of adds. Then we get to the output protocol, which takes a very similar form to the input protocol. First, wait some number of clock cycles for the receiver to be ready, then apply the calculated data to the output, let the receiver know the data is there, and go back and process another input. Very simple. If you go to any trade show presentation or have a discussion with any SystemC guru, you will undoubtedly hear terms bandied about that confuse you. Let me try and explain a couple of the more common ones. The first is the term metaport. In this diagram, we can see two blocks connected via a number of signals, and each block has multiple ports to connect those signals to. However, it's not uncommon to have many such signals, sometimes in the thousands, and the complexity of dealing with them gets out of hand. It's also evident that in many cases there are a number of signals that are related to each other. For example, they're the relevant signals in a particular ready-valid handshake. So to hide a lot of that complexity, multiple related signals can be encapsulated into a single metaport, and each block now only has to deal with connecting up a single signal to a single port. This has similarities to interfaces in System Verilog. Now, there are a lot of features of metaports, and I encourage you to go learn about them, but for our purposes here, metaports are simply a way to encapsulate multiple related signals into a single entity to reduce complexity and clutter. TLM is another acronym that often causes confusion to the SystemC newcomer. TLM stands for Transaction Level Modeling. This essentially refers to how we move data from one place to another and depends on what kinds of interfaces we use between blocks. When writing design modules in Verilog RTL, you are transferring data from one block to another using what we here at Forte would call pin-level interfaces. This involves wiggling wires in detailed protocol implementations. When modeling at the transaction level, we can pass around entire coherent chunks of data via a single function call, rather than having to implement detailed pin-level handshakes to transfer that same block of data piece at a time. The key benefits here are improved abstraction and significantly higher simulation performance, since there are many less events in the TLM simulations. The penalty is accuracy of those simulations with respect to time, i.e. the TLM simulations are not cycle accurate. As an example, imagine I had a block that needed to process a JPEG image. If modeled at the pin level, I would ask my interface for the image and it would arrive perhaps byte by byte over a period of thousands of clock cycles. If I modeled at the transaction level, the entire image would arrive instantaneously in 0 clock cycles. Less timing accuracy, but very easy to write since I didn't have to implement the pin level protocols, and the simulation time is very fast. That's the end of our brief look at SystemC, but if you're looking for more information, Forte provides a free SystemC training course on our website. This course can be found at forteds.com/systemc. Please pay us a visit and learn more about this up-and-coming design language. I encourage you to look at it with an open mind. It's not really very difficult to learn, and most of the concepts are very similar to those offered in System Verilog. I hope this presentation was useful to you, and thanks for listening.